In this example, we're given an integral in polar coordinates, and we're asked to interpret this integral as the volume of some solid region E in three-dimensional space. I said polar coordinates, but I mean cylindrical coordinates because there is a z coordinate here. Remember that the volume element, dv in cylindrical coordinates, is the area element in polar coordinates times the length element, dz, in the third dimension, and that this area element is r, dr, d theta. Of course, dz is still there, and the order of these three differentials can change, but the point I'm trying to make here, or remind us of here, is that this factor right here of r is part of the volume element, dv. So this whole thing right here is just this is a triple integral over some region E of 1 dv. And so it is indeed a volume of something. The question now is, what is it the volume of, and then can we actually compute that volume? So let's start by trying to interpret the bounds as surfaces or functions in three-dimensional space. The innermost integral, remember the r is just part of the dv, we can ignore it for the sake of what we're going to do here with the limits of the integrals. The first integral working from inside out says that z varies from 0 to r squared. And so as we write down these formulas, I'm going to try to sketch some of these surfaces. And I'll sketch them in Cartesian coordinates, but remember we're thinking of these in cylindrical coordinates. So z equals 0 is just the xy plane. So our surface is either bounded above or below by the xy plane. And then z equals r squared, that's a paraboloid. So that's the paraboloid that goes through the origin and has just standard kind of width here. And so once we have these two boundaries, now we know that our solid is bounded between the floor and this paraboloid. Okay, the question now is how, so where is it bounded in between these two? And so that's where we work out we work to the next integral. So the second integral tells us that r varies from 0 to 2. And remember, r and theta, those are polar coordinates in the base. So r varying from 0 to 2 tells us that our r is going to start at the origin and work out until it gets to a length of 2 in the positive x direction. That's how r is traced out. And we still don't know exactly. We know that at least this portion of the curve of the parabola right here, at least that portion, this sheet right here, at least that much of this is in our solid. And the question is, how much more is there in the solid? And that's where the third and final integral comes from. And so this one says that theta starts at negative pi over 2 and varies to positive pi over 2. Okay, and so theta is measured in the usual sense. It's measured in the positive, from positive x direction to positive y direction. It starts at 0, and it's measured up to this way. So the angle that's in the direction of the positive y-axis, that's positive pi over 2. And we're going to get traced out a portion of our solid region here. All right, but then it stops. And to get to negative pi over 2, this magenta kind of fan that I've drawn here, this gets rotated in the other direction until it hits the negative y-axis, and the rest of this gets filled out this way. Okay, so the solid region here is exactly this. The solid region E is bounded in the background by the YZ plane. And in the foreground, there's a cylinder of radius 2. And then from top to bottom, it's cut out. It's like it's gouged out by this paraboloid. And the solid region is everything that lies in between the XY plane, the YZ plane, this cylinder, and then from above it lies underneath the paraboloid. Okay, so that's the volume, that's the region for which this integral is going to be the volume. Now let's actually compute the integral. So let's actually compute the volume. This is, by the way, understanding the region, in my opinion, is the hardest part of this problem. Computing the integral, is, especially when it's already given to us in cylindrical coordinates, computing the integral is just, for fun. It's the fun part. All right, so let's write it down and then work it out and enjoy it the whole time. So, as always, this is an iterated integral. We start from the inside. We integrate with respect to z, but there's no z's in the integrand, so this is just constant. So this gives us negative pi over 2 to pi over 2. Integral from 0 to 2. So this is, after integrating, this will just be z times r, and then we plug in for z. Z equals 0, z equals r squared. That just leaves us with r cubed here. dr d theta. And at this point, this integral is separable. So the integral that we started with was not separable because it had a function in a boundary of the integral. But we integrated that out, and it's gone, right? And so now we see the next integral we have to compute is only in terms of r. And if we want, we can just take this d theta over here and separate this integral out. And so this ends up being integral negative pi over 2 to pi over 2 of 1 d theta times the integral from 0 to 3 r cubed dr. This one is just the length of the interval, so that's just pi. And this one's going to be r to the 4th over 4. And then obviously plug in r going from 0 to 3. And 3 to the 4th power is 9 squared, so that's 81. So we end up with 81 pi over 4 for the volume of this region that we just worked out here, that we just drew.